Imagine a World War II battlefield where radar screens flicker unpredictably, radio messages arrive distorted, and long-distance communications collapse whenever traffic increases. Engineers respond by adding power, boosting frequencies, and reinforcing hardware, yet the failures only multiply. Signals interfere with each other. Noise overwhelms information. Feedback destabilizes entire networks. Without understanding why, militaries invest more resources into systems that become less reliable under pressure. This situation was not hypothetical. It reflected the condition of communication engineering before a fundamental limit was clearly defined. Years before the war, Harry Nyquist demonstrated that every communication system has a maximum information rate it cannot exceed without breaking down. Without this principle, radar coordination, radio command chains, and large-scale communication networks would not have scaled reliably during World War II. The war would still have been fought, but with slower decisions, higher error rates, and weaker situational awareness. Harry Nyquist was born on February 7, 1889, in Nilsby, a small village in Värmland, Sweden. The region was rural, with an economy based on agriculture and local trades. Industrial and scientific institutions were concentrated in larger cities, and Nilsby was not connected to technical centres. Nyquist's early environment offered limited exposure to advanced engineering or scientific work. His family background was not associated with engineering, physics, or mathematics. Available historical records do not indicate that his parents or close relatives worked in technical professions. His early education followed the standard Swedish school system of the period. There is no evidence of specialized technical training during childhood. In the early 20th century, Nyquist emigrated to the United States, part of a broader wave of Scandinavian immigration. The United States was expanding its electrical and telephone infrastructure at a rapid pace. Long-distance communication networks were growing faster than the theoretical understanding required to manage their constraints. Nyquist pursued formal education in electrical engineering and physics in the United States. His academic training emphasized applied engineering and signal behavior in physical systems. His studies focused on how electrical signals propagate through wires, circuits, and transmission lines, preparing him to analyze communication systems as they increased in scale and complexity. After completing his studies, Nyquist joined Bell Telephone Laboratories, Bell Labs. Bell Labs was responsible for improving the reliability and capacity of the American telephone network. Nyquist's early work focused on signal distortion, bandwidth constraints, and system stability in long-distance transmission. As communication traffic increased, engineers encountered interference and instability that could not be corrected through stronger signals or improved hardware. Nyquist's role was to identify the underlying causes of these failures. During the 1920s, Nyquist published technical papers on telegraph speed, frequency limits, and signal interference. He demonstrated that communication channels have a finite signaling capacity determined by bandwidth. When this limit is exceeded, signals overlap and lose distinction, regardless of power or amplification. This conclusion challenged the prevailing assumption that performance could always be improved by increasing signal strength. Nyquist also studied feedback behavior in communication systems. He identified conditions under which feedback leads to instability, producing oscillations that disrupt transmission. These analyses provided engineers with criteria to determine whether a system would remain stable as complexity increased. His work supplied design rules that reduced reliance on trial and error approaches in large networks. Although Nyquist worked in a civilian research laboratory, the problems he addressed later became critical during World War II. Radar systems, radio coordination, and command networks depended on the same transmission principles he had analyzed earlier. His contributions did not result in a single identifiable machine. Instead, they defined operational constraints that determined whether large-scale systems could function reliably under wartime conditions. Nyquist remained primarily an analytical engineer. His output consisted of models, limits, and stability criteria, rather than physical devices. These principles were absorbed into engineering practice through standards and design guidelines, often without direct attribution. By the time the war began, many engineers were applying Nyquist's work without explicitly referencing his name. If engineers had continued to push power and frequency without understanding these limits, how reliable could World War II communication systems realistically have been? Harry Nyquist's most important contribution to engineering was not a device, a machine, or a physical system. It was a rule that defined how fast information can be transmitted through a communication channel without loss. This work addressed a practical problem that engineers faced as early telephone and telegraph networks expanded. As message speed increased, systems began to fail in ways that could not be explained by hardware defects alone. In 1928, Nyquist published certain topics in telegraph transmission theory, a paper that examined the relationship between bandwidth and signaling speed. He demonstrated that any channel with limited bandwidth can only transmit a finite number of independent signal changes per second. If signals are sent faster than this limit, they overlap. The receiver cannot reliably distinguish one symbol from the next, even if the signal is strong and the equipment is functioning correctly. Errors appear because the system is operating beyond its capacity, not because of noise or poor construction. This principle later became known as the Nyquist rate. It established the maximum signaling speed at which information can be reconstructed accurately from a sampled signal. Importantly, Nyquist showed that increasing transmission power does not solve the problem once this limit is exceeded. Stronger signals still interfere with each other if they are sent too quickly. The limitation is mathematical and structural, not technological. At the time, this conclusion ran counter to common engineering assumptions. Many engineers believed that communication performance could always be improved through better amplifiers, higher frequencies, or more robust components. Nyquist's work demonstrated that these approaches fail when systems are pushed beyond their allowable signaling rate. His findings forced engineers to accept that communication systems must be designed around limits rather than ambitions. Nyquist's work extended beyond signaling speed. He also analysed feedback behaviour in communication systems. As networks grew larger, amplifiers and repeaters were connected in chains, creating feedback loops. Under certain conditions, these loops caused oscillations that destabilized entire systems. Nyquist developed criteria that allowed engineers to determine whether a system would remain stable before it was built or deployed. This analysis became essential as communication systems increased in scale and complexity. During World War II, communication and radar systems expanded rapidly. Radar stations relied on precise timing and sampling of reflected signals. Command networks carried large volumes of information under extreme pressure. Air defense systems depended on stable feedback loops to track targets and guide responses. In all of these cases, engineers were constrained by the limits Nyquist had identified years earlier. Radar pulse repetition rates, signal sampling frequencies, and filtering methods were all influenced by Nyquist's principles. If radar systems sampled signals too slowly, targets could not be resolved accurately. If they sampled too quickly without sufficient bandwidth, signals overlapped and produced false or degraded returns. The balance between resolution, speed, and stability depended directly on Nyquist's analysis, even when engineers applied it through design standards rather than original theory. Nyquist's stability criteria were equally important. Radar and communication systems used feedback to amplify weak signals and maintain control. Without predictable stability conditions, these systems could oscillate or collapse under load. Engineers relied on Nyquist-derived rules to prevent such failures, ensuring that systems behaved consistently as traffic increased and conditions worsened. Nyquist's work did not appear in wartime propaganda or public accounts of the conflict. It was embedded in specifications, training manuals, and engineering guidelines. His principles shaped how fast information could move, how accurately signals could be reconstructed, and how reliably systems could operate under stress. These constraints determined whether commanders received timely and accurate information or faced delays and uncertainty. Without Nyquist's contributions, wartime communication systems would not have failed immediately. Instead, they would have produced increasing levels of error as demand rose. Radar displays would have blurred under heavy use. Radio traffic would have degraded at critical moments. Decision-making would have slowed as information became less reliable. Nyquist's work ensured that systems scaled predictably rather than collapsing under complexity. Should the success of wartime technology be attributed to visible machines, or to the engineers who defined the limits those machines could not cross? When World War II began, military systems expanded faster than any communication network before them. Radar stations multiplied along coastlines. Command centers processed continuous streams of information. Naval and air forces relied on radio links, operating under heavy traffic and strict time constraints. These systems did not fail because of weak hardware. They succeeded because engineers respected limits that had already been defined. Nyquist's principles shaped wartime systems through engineering practice rather than direct attribution. Radar designers selected pulse repetition rates and sampling schemes that avoided signal overlap. Communication engineers constrained data rates to prevent distortion under load. Filtering techniques were designed to balance resolution and stability. These decisions were guided by rules derived from Nyquist's analysis, even when engineers applied them through internal standards rather than original theory. In radar systems, the consequences were immediate. Detecting aircraft or ships depended on resolving reflected signals accurately. Sampling too slowly reduced resolution. Sampling too quickly without sufficient bandwidth caused overlapping returns and false targets. Engineers had to choose operating points that stayed within defined limits. Nyquist's work provided the framework that made those choices predictable rather than experimental. Air defense networks relied heavily on feedback. Tracking, prediction, and signal amplification all involved closed-loop behavior. Without stability criteria, these systems could oscillate or collapse under changing conditions. Nyquist's stability analysis allowed engineers to design feedback systems that remained controlled as traffic increased and conditions deteriorated. This stability was essential for systems that operated continuously under combat pressure. Communication networks faced similar constraints. During major operations, message volumes surged. Commands, reports, and coordination signals competed for limited bandwidth. Engineers who ignored signaling limits would have produced faster transmissions that carried less usable information. By respecting capacity constraints, wartime networks maintained reliability even when speed was limited. The trade-off favoured accuracy over volume, a decision that influenced operational effectiveness. Nyquist's influence extended beyond specific systems. His work contributed to a broader engineering culture that prioritized predictability over maximum performance. Wartime engineers learned that pushing systems to their apparent limits often reduced effectiveness. Designing within constraints produced systems that scaled under pressure. This approach contrasted with earlier practices that emphasized raw power and higher frequencies without regard for stability. After the war, these principles did not disappear. They became embedded in post-war communication standards, early digital systems, and emerging computing technologies. Sampling theory influenced analog to digital conversion. Stability criteria shaped control systems used in industrial automation and aerospace. Information transmission limits guided the design of data networks long before the internet existed. Nyquist's work became part of the foundation on which modern technology was built. Despite this influence, Nyquist remained largely absent from public narratives of the war. His contributions did not produce iconic machines or visible victories. They defined boundaries that prevented failure. Success took the form of systems that worked consistently rather than dramatically. This type of contribution is difficult to visualize and easy to overlook in historical accounts focused on weapons and battles. Nyquist's case illustrates a broader pattern in technological history. Wars are often remembered for decisive moments and visible tools. Less attention is given to the invisible systems that determine whether information arrives intact, decisions are timely, and coordination is possible. Engineers who define limits shape outcomes without appearing in photographs or headlines. World War II was not decided by Nyquist alone. It was decided by thousands of engineers applying principles that prevented collapse under complexity. Nyquist's work mattered because it established what could not be exceeded. By defining those limits, he allowed engineers to design systems that functioned reliably when failure carried strategic consequences. When evaluating wartime technology, should success be attributed to the machines we see, or to the limits engineers respected to keep those machines working?